The finite element method is one of the numerical methods which is used to solve extremely complex problems. When I say complex problems, I mean that there is not a single governing equation or a governing differential equation which, when applied with the suitable boundary condition, gives you the exact result. For complex structures, you can think of structures which are made out of many different elements joined together. For example, if you have the skin of an aircraft fuselage, then you have a very thin metallic structure, which is the skin, or a sheet. It is attached to a number of stiffeners by means of bolts or rivets. And both these structures or both these elements behave in a different sort of way. You can, of course, make some approximation and get some kind of governing differential equation to solve a global problem. But if you want to look at localized problems, such as what happens to a single bolt when it is loaded under a certain condition, and this bolt is present at a certain location in the aircraft fuselage skin, then looking at these localized situations becomes more and more difficult with analytical approaches. So if you don't have a simple governing differential equation which is suitable to be solved for such a problem, then finite element method is one of the methods that you would turn to solve these problems. This numerical method is a discrete method. Discrete methods always require that a continuous system, or in our case we also call it a continuum, has to be divided into certain subregions which are called elements. Further, these subregions themselves have certain vertices at the ends of these elements, and those are called nodes, where the solution is actually calculated. So if you consider a structural mechanics problem, then the solution that we are always looking for is the unknown displacement. This unknown displacement is always calculated at the node. First, a continuous function is used to represent the approximate behavior of each of these subregions or elements, and each of these subregions are joined together by continuity conditions so that you can get a solution for the entire system. Now, we always start with an approximation function for each of these elements. Therefore, we also get an approximate answer. If we want to make the solution converge closer and closer to the best possible or the exact solution, then we need to work on our discretization techniques, make the mesh finer and finer, so the size of the element smaller and smaller, so that we can get the best solution possible for the entire system. Of course, if you also remember from the previous course, or if you did not follow the previous course, then a standard way of carrying out a finite element formulation for a certain problem was first to start with discretization, then to have an approximate function to describe the element behavior. Then you had to set up an equilibrium equation using governing laws. These could be Newton's laws or any other laws that would set up a basic governing differential equation. With that, you would get a local element matrix, where the local element matrix would have a certain number of degrees of freedom, which should coincide with the number of degrees of freedom at each node. Finally, you would assemble these local element matrices to get a global stiffness matrix for the entire structure. For the global stiffness matrix, you would apply the boundary conditions and the loads, and you would solve this problem with the initial conditions to get a solution. So when we started with discretization, having an approximate function with the nodes, and we got to the point of getting a local element matrix, we always represented in small letter k. And once we had the local stiffness matrix for all the different elements, we assembled them together, it resulted in a global stiffness matrix which was represented with capital letter K. So this was always the global stiffness matrix. To set up the equilibrium equation, we had the final solution for a finite element formulation, which is what I would like to stop with in this video. So for the finite element formulation, the equilibrium equation where Ku is equal to F had to be solved was always used as the final equilibrium condition for the global system. Here, K is the stiffness matrix for a structural mechanics problem. U is the displacement vector. This is the global displacement vector, and F is the load vector, which accounts for all the external loads that are applied in the or to the system from outside. No matter what, we always ended up, no matter which kind of element we had, how we discretized the system, whether we had a simple system that we discretized with rectangular elements or we had triangular elements, it did not matter. In the end, each of these would have a local stiffness, and when we put all of it together from every element that was joined together and applied the continuity conditions, we ended up with this finite element formulation or equilibrium equation for the system. The displacements are unknown when we know the external loads that are applied to the system, and the stiffness matrix that basically always dependent on the material properties of the system. We were able to solve for the unknown displacements at each of the nodes. These displacements were then used to find out the strains and following that the stresses for the elements. The thing that you must remember from this little recap is that this was representing a linear problem. So there was no dependence of the stiffness on any other parameter which actually changed in the system. So the stiffness always remained constant. There was always a load that was added externally which was already predetermined. So those kind of things did not affect the problem, which made it extremely simple to solve because the stiffness had to be calculated only once. Keeping that in mind, I would like to close this video and I will see you in the next one where we discuss linear versus non-linear behavior.